So
Rosa is continue with her third talk. Thank you very much.
talk. Okay. So today is when I actually get to speak about some original results. All of this is joint with Gonçalo Oliveira. And so let me start by sort of very quickly recalling what we've done so far. So there are kind of two ingredients to what I want to do and to what I want to say today. The first is Calabi's metrics on dn, meaning a disk bundle inside O of minus m. And the second ingredient is what I've been calling Dzerzhinsky's duality, or Dzerzhinsky's theorem, which says that if you have, so gk over scalar squared gk is Einstein if gk is Bach-flat. So I want to produce Einstein metrics by mixing both of these ingredients. So I crucially forgot to say that Calabi's metrics are extremal. So I want to use these two together. And why is there any hope of succeeding? Well, because as we have seen, Bach-flat plus Kähler is implies extremal. So we have extremal metrics. Maybe some of them will be Bach-flat, and then we can apply Dzerzhinsky to those. That's the rough idea. Okay, so what's really okay? So what's there to do? Well, first of all, we have to figure out the domain of the Calabi metrics. Then we need to sort of pick a Bach-flat among the extremal. I mean, just extremal won't be enough. And then we need to study the zero locus for scalar, because, well, you know, if you have a formula like this, it will only be defined where scalar is non-vanishing. So you need to figure out where scalar vanishes. And then if you can do all of that, you need to understand where the Einstein metric lives, that is its underlying space. Okay, so a similar program was carried out in the compact case. By Shen, Lebrun, and Weber, who used it successfully to construct a conformally Kähler Einstein metric on the following space, CP2 to blow up CP2 bar. It's one of the spaces that does not admit a Kähler-Einstein manifold, a metric. So it's one of the spaces where one would like to have an Einstein metric, but can't use Kähler methods. And they managed to find a conformally Kähler-Einstein metric. Okay, so the difficulty, so it's actually pretty hard to find their metric, and the difficulty was bullet 2, which means find back flat among extremo. But we kind of have a shortcut, and I'll tell you about it when it comes up. So let me just state our results, and then I'll discuss them and put them into context. Okay, so the first theorem is just a sorting theorem. It's where we sort out Calabi's metrics. So we sort of put them together in a nice package. So you can think of it like this. So fix an M, and so fix an M, and so for all A positive and SA real, there is an extremo Kähler metric on DM, which is a disk bundle in O of minus M. That is, it's a neighborhood of the zero section in O of minus M, which is how I was talking about it last time. So a neighborhood of the zero section always contains a disk bundle inside O of minus M. And such that, well, two things. This A is the volume of the zero section. And this S of A is the scalar curvature. Sorry, the scalar curvature restricted to the zero section. So it's kind of there's a two-parameter fate of extremometrics, and I'm framing them as such. Okay, so now the second theorem. Any questions about this first theorem? So the second theorem is the Einstein theorem. It says the following. So there's the case m equals 1, which is separate. And in this case, what we get is that, so for all beta in 0, 4 pi, there is an Einstein metric on, sorry, this guy, which is just the first Hertzsprung surface, with a cone angle beta at the divisor at infinity. Which already appeared in the last talk. Okay, so this Einstein metric is not smooth. It has a cone angle. Okay, so now for what do we manage for m greater or equal to 3. Okay, so in this setting, there are two Poincaré Einstein metrics, and I will speak about this in a while, but I want to state the theorem first. So there are two Poincaré Einstein metrics such that well, first let me tell you where. So on the disk bundle that I was discussing before, that is a neighborhood of the zero section in O of minus m. So whose conformal infinities coincide. Okay, and I owe you two things. I owe you an explanation for Poincaré Einstein and for conformal infinity. So okay, so this is sort of a way to package what we proved. And so I'll move on to talk about Poincaré Einstein metrics so that you can understand the statement. Okay, so actually, Poincaré Einstein metrics have been studied for a long time. They're sort of a very rich subject. Let me start with the definition. Suppose you have a manifold with boundary. And suppose you have a defining function for the boundary. Let me tell you what that is. You can guess, but oops, sorry. So it's a function which vanishes on the M, and it vanishes to first order on the M. Okay, this is a defining function. Now, G is said to be Poincaré Einstein if, first of all, G is well, I should say, oops, I should say G a metric, right? A metric on the interior is said to be Poincaré Einstein if, first of all, G is Einstein on the interior of M. And then second, this extends smoothly as a metric to the boundary. Okay, so it's an Einstein metric which is in 1 over rho squared at the boundary. That's what a Poincaré Einstein metric is. And I will straight out give you an example that I think will illuminate the definition and why we care. And it's an example with which you're probably familiar. The example is the following. So you have the n ball in Rn, whose boundary is the sphere. And consider the following metric. It's a metric you know, but I'm not sure if you've seen it in this shape. So it's this one. I don't know if you recognize it, but this is the Poincaré model for the hyperbolic metric. So it's Poincaré-Einstein because this quantity here is a defining function for the boundary of the ball. Okay, and well, why is it Einstein? Because it's the hyperbolic metric. Okay, so actually, this example, there are two things I want to take. Poincaré-Einstein metrics are always asymptotically hyperbolic in a precise way, which I won't state, are asymptotically hyperbolic, and in particular, they are always complete. Okay, so they as I've said, they have been studied for a long time. And there's lots to say about them. So let me just pick three things which are kind of relevant to me. First thing is there is local existence. Well, okay. Let me, before I start with that, I should say, well, I'll say that later. There's local existence, and this is a result of Pfefferman and Graham. So what does local existence mean? It means around the boundary. So they're given a boundary, if it's smooth enough, then there will be a Poincaré-Einstein metric defined in the neighborhood of that boundary. Okay, then the other definition which I want to make is conformal infinity. So in the setting of the previous definition, so rho squared G. So the problem is that rho, the defining function, is not uniquely defined. There are several defining functions for the boundary. So this rho squared G is not necessarily well defined, but its restriction to the boundary has well-defined conformal class. Right, and well-defined means independent of rho, and this is called conformal infinity. Okay, and the definition which I want to make, because I think the phrasing helps, is so G is called an Einstein filling of the boundary with its conformal infinity. It's called a filling because, well, that's what it is. Okay. So uniqueness. So the question is, the typical question is, in this setting, given sort of a DM with conformal class, is there a Poincaré-Einstein filling? That's the question. And I've just said that Pfefferman and Graham showed local existence. And Okay, so then existence is at least local. And how about uniqueness? Well, uniqueness fails. But we understand we sort of understand why and how. And let me sort of say a little bit about that. So the map, which takes Poincaré Einstein metric, so from the space of Poincaré Einstein metrics to the space of conformal classes on the boundary, is Fredholm under fairly general assumptions. And we can sometimes calculate its degree, and it's sometimes one. And all of this is due to Anderson, who has really, really nice work regarding this question. Okay, so the other thing I want to say about these Poincaré Einstein metrics is that they occur in physics through the ADS CFT, anti-de Sitter conformal field theory correspondence, due to Witten. So there are many things about these Poincaré Einstein metrics that physicists want to calculate explicitly to answer physics questions. Okay, so what we have in our theorem is a Poincaré Einstein filling, or we have two. Well, we have one. We have a Poincaré Einstein filling of the boundary of dm, which is where our Poincaré Einstein metrics live, and the boundary of dm is S3 mod Zm, which is the length space. So we have a filling of that, which we call Gm plus, and we have a cap for that filling, which is called Gm minus. Now, Gm plus is smooth. It's a normal Poincaré Einstein metric, but the cap is not smooth, of course, because otherwise this would be a trivial metric. It is either incomplete, sometimes it's incomplete, or it has itself a cone angle. Okay. Any questions? Okay, so what I want to say next is kind of the discouraging part of the story. So as it happens, Page and Pope had built had built Poincaré Einstein fillings for S3 mod Zm, and they look different from ours because they are in different coordinates. And the construction is simply different. They come up for different reasons. They come up from physics. But it follows from a result of Derdzinski, which I didn't mention, and some general remarks that our fillings must coincide up to isometry. They have to be isometric. Okay, so then the question remains, do we have any new metrics? or do we have just a different reconstruction of something that already exists? Well, so this brings me to my next topic. So one of the upshots of what we do, oh, I got a heart. One of the upshots of what we do is we include metrics with very different behaviors into one family. I mean, I didn't say enough about our construction for you to understand. I'll say a little bit more later on, but it's a fact. Our construction is in fact comes in a family of metrics, and they are kind of different metrics, and so we can study transitions, and we can study limits because of that. Okay, and there's a great interest in degenerating families of Einstein metrics. So and because of that, we set out to calculate limits in our family. Okay, so what limits and transitions? So what did we see? So there are two things I want to report on that we saw. Oh, okay. Okay, so so we get two sorts of interesting limits. So the first sort is in the n equals 1 case, the zero cone angle limit, which is kind of what people care about, is often what people care about when there's a cone angle, is the zero cone angle limit. So the zero cone angle limit is what's called the Chen-Tao instanton, which is, well, this means that it's Ricci flat. So it's special Einstein. It's actually Ricci flat, and it's conformally Kähler. And if you've paid attention to the archive lately, it's been very popular. So it's a catwalk instanton these days. It's been on several preprints. Okay. The second limit, which I want to mention, is actually, it's not a limit, it's a rescaled limit. So one of our rescaled limits is an Einstein conformally Kähler metric, which is conformal to a scalar flat Kähler metric. And if you remember Derdzinski construction only works in the set where scalar is non-vanishing. So this metric does not come from Derdzinski's construction. Okay, so as far as I know, it's new, but I mean, I think in this area there are many physicists trying to construct explicit examples, so it's dangerous to claim that something is new. It might be known, maybe someone in the audience heard of this. So as far as we know, it's new. But also I think it raises the question of, it raises the following question. So is this a good way to construct new Poincaré Einstein metrics? That is, are there, or Einstein metrics, are there, so more precisely, we know many scalar flat, scalar complete toric metrics. And the question I'm raising is, are any of those conformal to Einstein? And if so, are the Einstein metrics, they are conformal to new or interesting or whatnot? Okay, any questions? Okay, so oh, sorry. Okay, I want to say something else regarding to the theorem, which sort of concerns the m equals 1 case, the first bullet in the main theorem. I want to speak a little bit about Hitchin-Thorpe. Okay, so the Hitchin-Thorpe inequality is a topological restriction to the existence of Einstein metrics. The statement goes as follows. If you have mg Einstein, then it satisfies a topological constraint, which is the following. This one, and so these guys mean, so this means the Euler characteristic from algebraic topology, and this means the signature. I don't know if you heard of this, but this is what we call B plus, the number of minus B minus. B plus is the dimension of a subspace of H2, where, let's see, where star acts by the identity, and B minus where it acts by -1. So it doesn't really matter to me what it is. What matters is that it's a topological invariant. It just depends on the topology of M. This is Hitchin-Thorpe, and now actually Hitchin-Thorpe has been generalized to the cone angle setting. Which is my setting in the first part of the theorem. So for m equals 1, I get Einstein, we get Einstein metrics with the cone angle. And it has been generalized to the cone angle setting by Atiyah and Lebrun in 2012. And what their theorem says is that suppose you have an Einstein manifold with a cone angle. Well, it's always 4. Actually, I should have said that from the start. All of my manifolds are 4-dimensional, and Derdzinski only works in 4 dimensions. I'm only stating Calabi in 4 dimension, etc. So so suppose you have a 4 Einstein metric with cone angle along a 2 surface, which I'm calling sigma. Then it satisfies the following things. So the same quantity as in Hitchin-Thorpe appears, but now the right-hand side is no longer 0. It depends on the cone angle. And beta is the cone angle. I'll write that down. Okay, so the right-hand side depends on the Euler characteristic of this, and no, there's no. Let me check. Yes, this is right. So the plus minus, no, so the plus minus is here. And so we're beta over 2 pi, where beta is the cone angle. Okay, so this is their theorem. And in our setting, so in our setting, in our setting, which is that of this, we can calculate the Euler characteristic, the signature of this manifold, and all of that. And our 2-dimensional surface is the section at infinity, which is this. We know it very explicitly as well. You can calculate this by hand. It's kind of fun. So this is what it is. Then what this gives, so Atiyah, Lebrun ensure that the cone angle needs to be in between 0 and 10 pi. Okay, and we actually constructed Einstein metrics only in the 0-4 pi regime. So of course the question is, are there Einstein metrics with there's a regime missing with cone angle? Oops. in here, and I have no idea, and I don't know how else to construct them. There could even be scalar ones there. Okay. Any questions? The other thing I want to say is that, yes.
May I ask something? You
Yes.
mentioned Poincare-Einstein matrix, so I think that's for non-compact manifolds. So it's
Yes.
and this page metric is compact block of
Yes.
CP2. Yeah. Could you
So
clarify it a little bit? Yeah. Thank you.
So I will explain why, but the only setting where we get compact examples is m equals 1. And the price to pay is we have a cone angle in that setting. Except, so that's a good point. Except that 0 is in 0 for pi, not 0, 2 pi. 2 pi is in here. So one of the metrics in our theorem is actually smooth because a cone angle 2 pi corresponds to smooth. So this is it's the page metric. It was known a long time ago. So it's a conformally scalar Einstein metric in here, which is smooth, no cone angles. But it's the only one among our family on CP2, connect some CP2, which is smooth. All of the other ones have cone angles. Any more questions? Okay, so I would like to use the remainder of my time to say a little bit about the construction of these metrics, kind of a proof of the theorem. But in fact, it's you know, because it is a constructive theorem, the proof is really the construction. So I'm hoping that you'll find it interesting. Okay, so let me say a little bit about the first theorem. And the first theorem, I think I've said enough that if you work on my first and second lectures, you'd be able to prove it yourself. So if you remember, we had a symplectic potential for extremal metrics, which was like this. And we had an explicit formula for H prime that came from solving an ODE. So this was what the formula was, and we were calling this gamma of R. And R was just x1 plus x2. Okay, so if you remember to construct a metric, you need the U to be convex. So there's that to check, and it's actually surprisingly hard to check. But what's more is that the H needs to have the right boundary behavior, which I said last time is ensured by these two conditions. And now, once you impose, so there are 4 parameters in the polynomial gamma. And once you impose these two conditions, you lose 2 degrees of freedom. So you get 2 degrees of freedom, and you just need to figure out how to express them nicely. So use them for later, and we express them through the volume of the zero section and the scalar curvature at the zero section. Okay, so the point here is that there's only one difficulty, surprisingly, which is to prove convexity, and I won't say anything about that. It's a technical thing. Okay, so now let me tell you about theorem 2. Now for theorem 2, what we have to do is take the metrics from theorem 1. So first thing is take the metrics from theorem 1 and see where they are defined. What do I mean by that? I mean the following. So the zeros of H prime prime determine the boundary behavior, and the boundary behavior determines the moment polytope and therefore the manifold. Okay, so if gamma has more positive zeros, or has zeros greater than A, then we get an HM. Otherwise, we get an O of minus M. And a way to see that is through the polytopes. So I'm actually drawing the oops, I'm not, but this is I'm drawing the singularities of H. So there is x1 plus x2 is equal to A, and the other ones are x1 equals to 0 and x2 equals to 0. Now, if H vanishes, so this is the polytope of O of minus M. If H vanishes somewhere else, what I'll see is this, and then an extra facet. And this extra facet will give me an HM. And I sort of had said this before. It was one of the examples in the first talk. Okay, so then you need to decide what happens with regards to this. And then you need to impose Bach flat. And this is what I think. So we have a shortcut for that. What we do is we actually show that Bach flat is equivalent to extremo, which we already knew, but together with just the fact that the scalar of this metric is constant. Okay, it's sort of obviously a necessary condition, because if what's inside scalar is to be Einstein, it needs to be constant curvature. But what's interesting is that it's actually enough. And what is even more interesting is that we can carry out the calculations this way. So what was really difficult for Shen, Lebrun, and Weber is really not that hard if you do things this way, at least for us, because the scalar curvature is this. So we can do these calculations, and we impose the condition. Okay, what else do we need to do? Well, we need to worry about vanishing of scalar. We need to understand where, so first of all, whatever it is, it's going to be a line parallel to this side or this side. And we just need to see whether it's inside the polytope or outside the polytope to see if it's Poincaré-Einstein or not. Okay, so let me tell you, let me sort of summarize what we get in terms of bookkeeping. So first thing that can happen is so gamma has no other positive zeros greater than A. This means this means that the Bach flat is on O of minus M. Okay, so what happens to the Einstein? Two things can happen. First thing, well, scalar does not vanish. And this happens. And we get, what do we get? Well, we get incomplete metrics. We get incomplete Einstein on O of minus M. Okay, what else do we get? Well, it can happen that scalar does vanish. And in this case, what we get is two Poincaré Einstein metrics. One is smooth, the other was not. We are in this setting of the theorem, but Gm minus is incomplete. So let me draw the polytopes. What you see here is this. It's the polytope for, oops. Doesn't let me. It's this. Okay, what you see here is this, but with the vanishing of scalar. So there is one Poincaré Einstein here, which is the smooth one, and the one that's always paid, that's also page popes, and the other one is here. It's the cap. Okay, what else can happen? And then the other case is gamma has another positive zero greater than A. In this case, the Bach flat is on a Hertzsprung surface. Okay, and okay, here in this setting, you can show the scalar always vanishes. And what happens in terms of pictures or, okay, so you get the polytope for HM. It's kind of skewed, but it's this. It's really skewed, sorry. Okay, and there's always somewhere inside the polytope a vanishing locus for scalar curvature. One of the Poincaré Einstein metrics is this. It's the smooth one. And the other, the cap, is this one. And this cap has a cone angle, while this cap is incomplete. Okay, so you sort of get a geometric way to understand these page pope metrics and to cap them and whatnot. And so what you don't see in this schema is where the limits come from, but you know, it's just follow through the calculations precisely. Okay, so this is what I had to say. Are there any questions?
Page pop metric is non-compact example?
No, page pope is compact.
Compact.
It's the only, it's m equals 1. So it's the m equals 1 case where they're all compact but have a cone angle except the page pope one. So okay. I kind of, if you know the page pope metric well, then maybe a good way to phrase the first part of our theorem is page pope is included in a family of conformally Kähler-Einstein metric with cone angle. And it's the only zero cone angle one in that family. This kind of extending. No,
different than page metric, or it's
no, the same page.
They are the same thing.
The same thing, yes.
Okay.
Page. So there's Page and Page Pope. Maybe that's where so Page Pope is maybe not so famous a construction, and it's a construction for Poincaré Einstein. Those guys are non-compact.
Oh, okay.
So there's two constructions. Okay, it's confusing because Page is involved in two of them. So I think the most famous one is the Page metric, and it's Einstein and conformally Kähler just here. It's one metric, just one.
Okay.
And there's Page Pope metrics, which are Poincaré Einstein. So they're non-compact, they're asymptotically hyperbolic, and they are fillings. Their boundary is S3 mod ZM. It's a length space. And they are asymptotically hyperbolic. They're different metrics, but Page was involved in constructing both.
All right.
And they're both embedded in our construction. So
okay, so it's one of these Page Pope metrics can be rescaled to make the so-called Page metric, right?
No, so they live in different spaces. So this one is in H, it's in M equals 1. And all of these only work on M greater or equal than 3.
Oh, okay.
So I don't know if maybe there is, but I don't know of any way to build to build one from the other. And in fact, I don't even know of a way to connect them because the M's jump. We don't know how to go from 1 to 3 continuously.
Right. Yeah.
And unless we do it the formulas hold. If you find that interesting, maybe you can look at the formulas hold, even if M is not integer. You can, but I think it would be hard to give geometric meaning to that. Maybe that's an interesting question. I don't know.
All right. Yeah. Another question? All right. Thanks, Rosa, for this nice talk.